Lama pula. Okay. Alright, so today we will continue the linear amplifier application, which is summing for inverting, and also we will look for non-inverting as well. And then before summing, kita akan we will look also the difference, yeah. Oh, got one. Difference amplifier or subtractor amplifier as well, okay? And then we will proceed with the non-linear amplifier applications, which is comparator and the Smith trigger, okay? All right, so just quick revision, okay? Quick recap from yesterday's class. So this is the ideal op-amp characteristic, where for ideal op-amp characteristics, we have a high open loop gain. Okay, we have high open loop gain, where in this high open loop gain, the gain is very infinity, reach to infinity. Okay, and also the input impedance. Okay, this is the input impedance. The input impedance is very high, so due to that, okay, currents cannot enter this op-amp. All right. So due to the high input impedance and high gains, we also gonna have low output impedance. Okay, the output impedance is very low, which is near to zero. Okay. So how to calculate voltage at the output? Voltage at the output can be calculated. VO equals to A, which is the gain, right? And then V plus minus V minus. What is V plus? V plus is at the non-inverting, betul kan? Non-inverting terminal, and the V minus is at the, this is the V minus, which is at the inverting terminal. Okay. So it's written here, yeah. So the plus or the positive terminal is called as non-inverting, and the negative terminal is called the inverting. So look at the signal input. If the signal input is at the negative terminal, we call the configuration, it is a non-inverting configuration. If the signal input is at the non-inverting, someone just join us. Okay, so if the signal input is connected to the non-inverting terminal, so it will be non-inverting configuration. So look where the signal input is, so it will gonna be that input configuration. All right, and then the output saturation voltage plus minus VO saturation is equal to the input supply voltage, which is plus minus VCC. Okay, so this is the plus minus VCC or VEE. Yeah? Plus VCC minus VEE. Okay, so what is this? VCC and VEE is the DC supply. So the output, the output voltage will depend on the this DC supply. Okay, so it cannot go more than the value of this DC supply. Okay, for example, if the DC supply is 12 volts for the positive value, so if the input is positive, it will saturate at the 12 volts. Yeah, it can't go more. Apa punya dengan sebelah aja ya. Okay. So same as well. If the output voltage is a minus value, okay, is minus value. So it will not go more than the value of minus VEE. So let's say the value of minus VEE is minus 12. So it will not go further than minus 12, even though it can increase. So it will be saturate at minus 12, right? So the output voltage, the waveform at the output voltage is always square wave, yeah. So this is will not it have a high CMRR. CMRR is the common mode ratio. Okay, I think this will not come up in your exam. Okay, and also high bandwidth. This is for your extra information only. So if you want to analyze the common circuit of op-amp, okay, first you have to put in mind that no current can enter terminals V positive and V minus, okay, because due to the high input impedance, so no current will flow here. So since that no current will flow here, the value of the V plus will always same with the value of V minus. Okay, so if V plus is 0 volts, yeah, V minus also will be 0 volts as well. Okay, so if V plus is the input voltage, so V minus also will equal to the input voltage. So it depends, yeah. And then, so this is just same as just now. In a circuit, V plus is forced to equal to V minus, and this is called, as I mentioned just now, this is called a virtual ground. Okay, and the supply DC voltage here, the VCC and minus VE here, we call this as rails. Yeah. All right. So yesterday we have looked for the for the linear applications. Okay, we have looked at the inverting amplifier. Okay, where the input signal is at the inverting terminal here. Okay, which is at the negative terminal, and we have derived the equation where the V output will be minus R2, R1, and times with the input value, voltage input value, right? So for the non-inverting amplifier, why it is called as non-inverting amplifier again? Why? Because it is the signal input is at the non-inverting, which is at the positive terminal. Okay, so we also have derived yesterday the equation if you want to find the value of the voltage at the output. Okay, so it will be 1 plus R2 over R1, okay, times with the input value of voltage input value. All right, and we also have looked at the voltage follower or unity follower where the output value is same with the input value. Okay, so V output equals to V at the minus, which is equals to the V at the plus, which is equals to input value, all right, V output. Okay. So again, yeah, zero impedance here, zero impedance, zero output impedance. Okay, zero output impedance and infinity zero output impedance and infinity input impedance. Okay, for op-amp, and it will cause the output volt. It will not cause zero output voltage at all. Okay, there is output voltage will come out. So the output voltage is depending on the gain times with V plus minus with the V minus voltage. Yeah. All right. So op-amp linear applications. Okay. So we will continue from yesterday. Difference amplifier or subtractor. Have you tried to figure it out? This equation? Any of you have tried to derive this equation? Did you get like what did I get? I showed here. Tak ada. None. Yeah, try. None, try. Okay. Okay, so let's look here. So the difference amplifier or subtractor, you can see that there is a two voltage supply here, which is V1 and also V2, okay, which is each of them has connected with the resistor R1, but at the non-inverting terminal, there is a parallel circuit, okay, a parallel resistor connected, which is R1 and R2. And then at inverting terminals, there is another feedback here. There is a feedback, negative feedback, which is connected at the output voltage here, which is R2 resistor. Okay, so if you get this types of configuration of op-amp, it is known as difference amplifier, and the formula at the V output will be V output equals to V1 minus V2, and this value you should times with R2 over R1. Okay, how this equation will not be given during your exam. Okay, this equation will not be given during your exam, and it is better for you to derive from this circuit. Okay, it is better for you to know how to derive from the circuit, because it is quite complicated for you to memorize this formula, right? So how? So first of all, if you want to derive this equation, first look at this point first, yeah, at V1. Look at one by one, yeah, right? So at V1, okay, I is equals to V1, this potential difference, okay, minus with this positive here. This is non-inverting terminal, so which is V positive. So this V positive is same. At this point also will be V positive. And at this point, since this is the inverting terminal, so this is going to be V minus, all right? So first of all, let's look at the V1 root, which is at the non-inverting terminal one, yeah? So first, for you to measure the currents that flow here, so it will be V1 minus V plus over R1, okay, over R1, which is this current is same flow with this current, okay, since that currents cannot enter this op-amp inside this op-amp device. So the current that flow here is same with the current that flow here is same with the current that flow here, same with the current that flow here, all right? So it means that equals to V plus minus 0, okay, because this is ground, over R2. So you can rewrite this equation again. It will be V1 minus V over, which is this here, V plus. Sorry. How to undo it again? I need to erase it. Yeah. Erase it. So I need to erase this. So you can rewrite this equation. Okay, so V1 will be over R1. Okay, and then V plus over R2 plus V plus over R1. Okay, and then you can factorize it. It will be 1 over R2 plus 1 over R1. Then it will be V1 over R1, still here. Okay, so again, this we have Allahu Akbar. Okay, we need to accept this. Okay, so again, we have what mentioned earlier, that V plus is always equals to V minus here, right? So let's put the value same, which is V. Okay, so this is V, this is V. Okay. Tak jadi, curi mata ni. Oh, tak boleh, kena pilih juga dari sini. Okay. So instead of writing this V plus and V minus, So let's write V. Okay, so it's going to be easier. So V1 over R1 equals to V over 1 over R2 plus 1 over R1, where this is also equals to R1, R2 over R2, R1, right? So V1, R1. So since that we don't know the V, we don't know the V here, make it as the main, as the main. So it will be V equals to V1 R2 over R2 plus R1, okay, because you bring this to here. Okay, so you will get the V value is V1 or R2 over R2 plus R1, which is at V1 here. Okay, so once you settle at the V1 here, let's proceed to the V2 here. Okay, so at V2, okay, I value is same, yeah, since that there's no current flow inside the op-amp, so the flow of current here and here is same. Okay, so I is equals to V2 minus V, this is V2 minus V over R1, which is equals to V minus V output, yeah, V minus V output over R2. So rearrange this equation, you will get, okay, rearrange this equation, you will get that V out, okay, V out equals to V1 R2 equals to V1 R2 over R1 minus V2 R2 over R1. Okay, and you can factorize it, and it will be V1 minus V2 R2 over R1. Okay, where the value of V here, okay, you can replace the value of V here with the value of V at that we have found just now. Allahu Akbar. Sekejap ni. V that we have calculated just now, which is this. Okay, put inside here. And the last, you will get the value of the V output. Okay, V output, which is the one that we want to figure it out, which is equals to V1, V1, okay, V1 minus V2 times R2 over R1. Okay, I hope it's clear. Okay, I hope it's clear, and you can try this again. Okay, because I didn't do this step by step for at V2 here. Okay, so try to figure it out how to prove this equation. Okay, so this amplifier is known as difference amplifier. What is the usage? What is the application of this difference amplifier, or also known as subtractor amplifier? So it is useful for solving various mathematical equations. Yeah, so this kind of configuration is very useful to solve, okay, mathematical equations. All right. So next, let's look at the summing amplifier. Okay, summing amplifier, it's quite complicated because you can see that the input signal is not only one input signal, but it has three or more. It has more than one input signal. Okay, usually that is called a summing amplifier. All right. So summing amplifier, it can be divided into two types, which is inverting or non-inverting. So in inverting configuration case, where the input signal is connected at the inverting terminal. For non-inverting configuration, summing amplifier, the input signal is connected at the positive terminal, which is non-inverting terminal. Okay, so please remember, yeah, the summing amplifier. What is the difference with the inverting, common inverting and non-inverting amplifier? Is it has more than one input signal. Okay, it has more than one input signal at the specific inverting or non-inverting terminal. Okay. Okay, so kalau if difference amplifier, it also have more than one input signal, but the input signal, okay, but the input signal is at both, yeah, which is at the inverting and also at the non-inverting. Both have input signal, so that is difference amplifier. But for summing, they have only one input signal, but the input signal have one input signal at one specific terminal, but at that specific terminal, it has multiple values of input voltage. Okay, input signal, input voltage. Yeah. All right. So for this case, let's look at the summing amplifier for the inverting configuration first. Okay. So there is a resistor here connected at the negative, which is at the inverting terminal, okay, which is also known as feedback terminal, okay, as I think you all know that. Okay, so recall the inverting amplifier, okay. So to solve this this summing amplifier, you have to recall again the one that we have learned yesterday, the inverting amplifier, okay, where IF, okay, is equals to I1, I2 and IN, okay, right? So for yesterday inverting amplifier, IF, the currents that flow at IF is same with the current of flow that I1, right? But since for summing amplifier, it has multiple input of signals, so the IF will be equal to I1 plus I2 plus IN, since that this is also parallel, so the flow of IF here is same with here. All right. So how to get this this kind of equation? Okay. So same as inverting amplifier, IF, since that IF, kalau inverting amplifier, IF is equal to I1, right? And this I1 is equals to V1 minus 0 over R1. Okay, I hope you still remember about yesterday's class. So since for this summing amplifier, it has a few numbers of input signal. So at I2, okay, I2 will be V2 minus 0, yeah, because this input is 0, V plus is equals to 0, so V minus also will be 0. So here is 0 and here is 0 as well, over R2. And also same as IN2, IN it will be Vn minus 0 over Rn. Okay, so you just put all this inside here. Okay, it will look like this. Okay, it will look like this. Okay, someone just joined us. Okay, so if R1 is equals to R2 is equals to Rf, if this all value of resistance is same, okay, you can cancel. Okay, you can cancel all this all this resistor value here, since that the value of Rf and R1 is the same, so you can cancel the value and say it will leave out only V out equals to minus V1 plus V2 plus Vn. All right, so this will be the final formula for V out. Okay, for summing amplifier in case of inverting configurations. So when to use the summing amplifier, or what is the usage of summing amplifier? Okay, so summing amplifier is a good example of analog circuit serving as analog computing amplifier. So summing amplifier is used for analog computers. Okay, it is very useful for analog analog computers. Yeah, and so analog circuit, yeah, this is just for additional note. Analog circuit can add, can subtract, can multiply, can divide, okay, using logarithmic logarithmic components, differentiate and integrate as well, okay, in real time and continuously. So this what is the when I say analog circuit, this is what analog circuits can do. It can do the logarithmic components. It can add, subtract, multiply, divide, and all those things. Okay, even differentiate, integrate, and all those things as well. In real time. All right. Okay, so let's look at a summing amplifier for non-inverting configuration. Right. So for this configuration, same as the inverting, you have to recall again the non-inverting amplifier, which is V out is equals to R1 plus RF over R1 . Okay, RF over R1 times V in, kan? V in or V plus, right? So for this case, so V out, this what we got from the earlier, from the what we have derived yesterday, which is from the non-inverting amplifier, okay, which is right, which is here, okay, which is non-inverting amplifier here. So, but in this case, V plus, okay, in this case, we cannot use straight away this because we don't know what this V plus is. So V plus is equals to here, right, which is there is a parallel resistor which is RA and RB. So how to do how to solve this parallel resistor here? You need to use superposition theorem. Superposition theorem. So for non-inverting, it's quite complicated a little bit compared to the inverting one. So for non-inverting, you need to use superposition theorem to get the value of V plus here. So what is superposition theorem? Okay, so superposition theorem, same as Thevenin theorem, but Thevenin theorem, you will get the value of V voltage Thevenin and R Thevenin, right? You will get you will replace the multiple or the linear resistance with R Thevenin, and also the linear voltage will be V Thevenin, right? But for superposition theorem, okay, the linear circuit have more, when to use superposition theorem, when the linear circuit have more than one source. Okay, when it has more than one source. So what you're going to be, you have to assume that only one source it can be used at a time. Okay, for example, just focus on this part. For example, at this part, minus, this is positive. Let's assume that in this case, VB is equals to 0. Okay, let's assume that VB is equals to 0. So when VB is equals to 0, it will be ground here, right? So VB akan ada ground, VB will be ground, so it will be look like this. So this is RA, which is VA here, and VB will be ground. RB here, and VB, since it ground, it will be 0. Okay, since it ground, it will be 0. So at this part, let's solve this part first, which is VA. Okay, VA is equals to, okay, VA will be equals to RB over RB plus RA times with VA. Okay, it will be VA plus here, yeah. Sorry, it will be VA plus here. Dekat sini will be VA plus. Okay, VA plus, yes. Dekat sini will be VA plus for this configuration when VB is equals to 0. So for VA plus, it will be RB over RB plus RA times with the BA. I think this one I don't have to explain because I think this is very basic. It seems like how you solve the Thevenin theorem here. And then you can finish there. You have to consider another thing, which is if VA here is ground or VA here is 0. Okay, so when VA is equals to 0, what will happen? Okay, what will happen? The circuit will gonna look like this, right? This will be ground. Okay, any will be ground. This will be ground. This is RA, and this RB. There will be VB both, VB source. So at this point, it will be VB plus. Okay, so VB plus. How to calculate VB plus? VB plus will be RA over RA plus RB times with VB. So now you have two values at this point, which is VA plus and VB plus. So how to get the total of V plus here? So V plus will be VA plus plus value of VB plus that you have calculated just now. Okay, so put together the value and rewrite it again, and you will get this kind of equation, right? So if you get confused where this equation come from, so this equation come from the superposition theorem, which is at this point, okay, where for you to solve using superposition theorem, you need to consider one of the voltage source will be grounded, okay, which is the first case. We assume that VB is equals to 0 or VB is grounded. So at this point, okay, it will look like this. Okay, it will look like this, and at this point, V plus will be VA plus, right? VA plus. So VA plus, okay, you can solve this this configuration. You will get RB over RB plus RA and times with VA. And then you have to consider another condition where if VA voltage source is grounded or equals to 0. Okay, so at this point, V plus will equal to VB plus. So solve this configuration, you will get VB plus equals to RA over RA plus RB times with VB. Okay, so which value you have to use, which between VA plus and VB plus? For VB plus, you have to use both. Yeah, so VB plus will be value of VA plus VB plus. Okay, so take these two value. Okay, take those two value, and you will get this equation. All right. So when you get this equation, VB plus equal to this value, replace inside the first equation where there is a V plus. So you will get the final equation. It will be like this for V output. Okay, so if you want to measure the V output, these are the formulas. Okay, this is the formulas for non-inverting. Okay. All right, I hope up until here is clear. Any questions? Do you have any questions up until here?
Masih okay, Sensei.
Okay. All right. All right. Okay, so if okay, let's proceed. Okay. So it's quite challenging kan, kelas pagi-pagi.
Nampak ni tak okay dah.
Nampak ni tak okay, but then suddenly yang ni okay. Okay, so this is exercise 1. Okay, so exercise 1, name the function of each op amp. Okay, so the function of each op amp. So so this part, sorry, this part. For this kind of op amp, yeah, dia memang akan bagi I need to delete this first. It will be very complicated. Okay, it is purposely make complicated. We are to make you confused, but the basic is same with the previous one. Okay, which is you have to look. You need to kena cut sikit. For example, first of all, solve this part first. Okay, solve this part first. Okay, which is what configuration is this? This is inverting or non-inverting amplifier? Inverting kan? Okay, so very good. So this is the inverting amplifier, right? So this is inverting amplifier because it is the signal is at the inverting terminal. Okay, so already in mind, right? The inverting formula. So to solve the inverting formula, it will be, let's look back, which is this equation, right? V out is equals to minus R2 over R1 times with V in. Where is this slide just now? Alamak, dah terlalu jauh dah. Exercise. So for this one, the value at this point, yeah, V out is minus R2 over R1, which is this is R2, this is R1, times with the value here, V in. Okay, nanti masukkan aja. You just have to replace the value and then you will get the V out here, the value of V out here at this point, right? And then since that this is, you get this value and there is a resistor, you can find the I here. So this, let's say this is going to be I1, okay? It's going to be I1. Stop there. Okay, once you get the I1, you stop there. Let's proceed with this configurations pula. So this configuration, what is configuration is this? This is unity. Okay, unity. This is unity or voltage follower. So voltage follower for unity is very easy, where V output is equals to V input. So no calculation needed here. So the value of V output here is same with this input value, which is 2 volts. So 2 volts, you can calculate with, you get the value of voltage, you have the value of resistance, so you can get the value of I here. So let's name the value of I here, I2, I here is I2. Okay, so stops there. And then let's proceed with this configuration pula up until here. So what configuration is this? This is none. Okay, this is non-amplifier. So this is non-amplifier. So what is the formula? So for formula, V out is equals to 1 plus RF. Wait, R2 plus R1 kan? This, right? 1 plus RF over R1 and V input. So 1 plus RF over R1. This is RF. This is R1. Okay, this is RF. This is R1. And then so but be careful. First of all, the V plus here, you have to, there is a resistor here. So get the value of V plus here, the value of voltage at this point here first, yeah. So the value will be the current here will be it's reducing a bit, but the value of voltage is the same. Okay, the value of voltage for this point and this point, yeah, same. Okay, so it will be V in here. So V in, get the value of V in first from here. Okay, and you will get the value of V out here. So V out, once you get the value of V out here, you can calculate the value of currents here. So let's consider the value of current here is I3. So I that flow here is equals to I1, I2, I3. I1, 2, 3. So once you get the value of I here, okay, once you get the value of I here, then you can solve this configuration pula. So this configuration, identify what configuration is this. So you will get the configuration here. After you identify, you can proceed with the formula like this, okay? And next, you can find the value of VO4 here. So kalau kat sini, you already have the value of VO1. Okay, you already have the value of VO2. You already have the value of VO3. And from here, you can already have the value of VO4. Okay, once you identify what's the configuration it is, use the formula, and then you can get the value at this point. Okay, once you get the value of at this point, okay, you need to know the currents here because there is a resistance here. So once you get the currents here, flow here, and then you can proceed with this one, with this, which is this is the difference configuration, and you will get the value of VO5 here. So kalau macam ni kan, if you in exam, it will give like this kind of configuration, which is kalau sekali tengok, once you look at it, you look like we didn't learn at all. Tapi once you look one by one, okay, do it one by one, it's actually is what is the combination of all configurations that we have learned before. Okay, and so that's why it is very important you understand those configuration first, this basic configuration first, and then we can solve these questions. Okay, so these are the answers. Okay, later on, can you try and can you check whether you will get this answer or not, right? So these are the answers for the for that exercise, right? So let's go to the next one. OP-AMP non-linear applications. So yang ni dah masuk to non-linear application. So linear application, is it okay? Kalau nak check okay ke tak, you need to if you want to check you okay or not, you understand well or not, you need to solve this question. So if once you can solve this question, means that because this is very basic, okay, because this is very basic, it means that once you can solve this equation, then it means that you already master linear applications. How to find for VO4? Where's VO4? Oh, VO4 is here. Okay, so you already have the I1, I2, I3. So you get the value of I here. Okay, so what is configuration is this? This is the same with this configuration, right? This is the inverting configuration. So for inverting configuration, all right, so for inverting configuration, you should use this formula here. Okay, so you have your R2, you have your R1. You don't have your V in, right? Your V in is, but you have your value of I. Okay, you have the value of I. So V, you have the value of I here. And since that you have the value of I here, so V is equals to IR, right? Okay. For this actually, okay, for this actually, V is equals to IR, kan? V is equals to IR. So resistance, what is the total resistance here? Don't look here, we forgot here because here is already solved. So look at the total resistance here. 1 over R plus 1 over R plus 1 over R. Okay? 1 over R plus 1 over R, 1 over R. So inverse this one, right? 1 over R inverse. So you will get the total value of R here. You already have the value of I here. Okay, so you can get the value of voltage here. So once you get, you get the value of voltage here, so this will gonna be the V in. Okay tak? Go. V in is 2 volts right 4. V in is 2 volt right for 3. For VO3 ke? Betul?
For the
VO3 or VO4?
VO3, the
VO,
V in
uh-huh.
dia lepas yang 0.5 K punya resistor tu, lepas tu situ dia tak tolak apa-apa voltage kan? Ke ada
Sekejap I check. Sekejap I check ya. Where is my RF value, R1 value. No, dia tak tolak apa-apa voltage. Why? Sebab voltage, so you have to remember again, kena go back to the basic. Voltage kan for apa tu? We have linear, we have parallel and we have apa parallel, apa satu lagi? We have parallel and we have apa ya? Parallel dengan, bukan linear kan? Parallel dengan apa configuration satu lagi? Series configuration, yes. For parallel and series. For series, all the voltage at each point, and any point, sama. Okay, for example, tak kira lah berapa banyak resistor, no matter how many resistor that you have. For this voltage, for example, the supply voltage is 5 volts. You measure here, this is also 5 volts. You measure here, this is also 5 volts normally. Okay, unless there is a output here, output gonna be different. Tapi kalau dekat sini, resistor series, the value of voltage is always the same. Okay tak? Okay tak? Kalau output nanti baru you have to plus all this resistor, then the output value of voltage is different. Tapi in the line, the voltage value is always same for series. Okay, so sama saja. So you have to use these 2 volts lah. Okay, all right. So once you get this, so here, then you can get the value of voltage here. So once you get the value of voltage here, nanti boleh kira pula for VO4. Okay, you can calculate for VO4, and then you will get the value of VO4. Same for this VO4, for these things as well. Okay, so this is also same with the VO4 value. Okay, so at this point, okay, and then boleh jadi, so this be careful lah for this part, for the last part, for the difference part, dekat sini there is a series here. No, sorry, not series, this is a parallel. Dia ada VO4, 1K, and then parallel and connected to this. Okay, so it means that this circuit and this circuit is parallelly connected. Okay, patutnya it should be if in a basic circuit, this value of current is same with this value of current kan, but in this case it's divided into 2, which is parallel connected with this VO4. So you have to consider this as well. Okay, so this is quite complicated sikit for this difference. Okay, nanti try. Okay, I want you to try. So the answer is here. The answer is given here. So this is 6 volts. Okay, so later you can check, because this is very basic. It's actually basic with the op-amp linear configuration, and also with the series parallel that you have learned before during your high school, right? Okay, so shall we proceed to the comparator circuit? One hour dah. Kita proceed Okay, kita proceed to the comparator circuit. So this is the comparator circuit. For comparator circuit, it is a non-linear applications. For this kind of non-linear applications, it is, I think, very simple. They're simple sikit compared to the linear application, because for non-linear, there is no mathematical, mathematical calculation, but there's still a little mathematical application for you to calculate the trigger point, the upper trigger point or lower trigger point, but not as many as linear applications. Yeah, so only one formula lah you have to know, which is later on this formula. Banyak ni inside this all slide. Only one formula, which is during on smooth trigger, only this formula. Okay, so I think for comparator, the formula is not so many formula that you have to remember. Okay, but you need to know how, instead of knowing the formula, you need to know how to draw the output. The output voltage, the waveform of output voltage. Right? So let's look. Okay, comparator circuit. So comparator circuits, as it name, the name is compare. Right? Comparing. So it's comparing two input signals. Okay, where one of them is always a fixed signal. So fixed signal ni usually we called as reference signal. Okay, so this we know that op amp, they have two input kan, and one output. So in that two input, one is always fixed. Okay, kalau ni Hong Kong we call IT. Okay, one is always fixed, which is, that will be our reference signal, and the other one is variable. It can be changed. Okay, and this input signal is usually the sine wave lah. Okay, in the sine wave. But both of them, these two of them, both represents a voltage. Okay, both of them will represent a voltage. Okay. So the name of comparator op amp, this op amp will compare these two between these two signals. Okay, and it will come out at the output. All right, it will represent at the output here. So the circuit compare the input signal with known as reference voltage applied at the another terminal, which is at the reference here. Yeah, the input here will always compare with the reference here. Okay, and it will produce either, okay, at the output here will always either high or low output voltage. Oh, someone just joined. Okay, some produce either at the output here will produce either high or low output voltage, which is depend on the input here. Okay, which is it depend on the input here after it's compared with this reference here, right? So the output always in saturation. Why it is always in saturation? It is because, okay, patutnya if you think, yeah, the output can go very far further. For example, if the V input is more than V reference, okay, if the input is more than reference, it will go further higher. Further higher, yeah, the output can go increase. There is no limitation. So that is where these two DC supply voltage we're gonna play a role, where it will control, it will limit the output voltage will not exceed than this DC voltage supply. Okay, for example, if the input signal is higher than the reference signal, okay, in inverting configuration, the output signal will based on this plus DC signal. Okay, will place on this plus DC signal, and it will be controlled by this value. So it will limit at 10 volts. Okay, it will limit at 10 volts. Yeah. So maximum it can go until 10 volts. The minimum it will go minus 10 volts. Okay, minus 10 volts. All right. So the function of this DC supply is to limit the output voltage. So it will make the output will become always in a saturation mode. Yeah, this is the saturation mode. So because of that, because of this saturation mode, it will make the output signal will always as square wave. Okay, because of this saturation exists, okay, due to the limitation from the DC supply here, it will make the output signal always square wave, yeah, no matter how the input signal is. Okay, usually the input signal is sine wave or triangular wave, but usually it is common with the sine wave. Okay, no matter how the input wave is, the output will always be square wave. Yeah. So the output of op-amp indicates whether the input the output of the op-amp indicates whether the input is greater than or less than, okay, greater than or less than the reference voltage, but it will not indicate the amount by which it differs. For example, what does that mean? It means that from this output, okay, you can only know at the output here is the value is greater than the input or lower than the input. Okay, for this case, let's say lah the input here is 5. Okay, the input here is 5 and the reference is a 2. So since that 5 is bigger than 2 for inverting configuration, so it will make the output become the maximum value of positive DC supply. Okay, and it will represent only that, but you don't know the from the output. If you look at the output only, you don't know how much is the difference between the reference and the input value, the input. Okay, if you look only at the output output waveform. Okay, so from this output waveform you can only know that it is greater than or lesser than, but you don't know how much it difference. Okay, sebab dekat sini, for example, yeah, if I apply just now I mentioned 5 and the reference is 2, okay, the output is still will represent as 10. It will not represent the difference here, which is 3, right? 3 volts. So by looking at this output, you don't know actually how much is the value of the difference. So if you want to know the value of the difference, actually you need to look at the input waveform here. Okay, input waveform or the original circuit configurations. Yeah. So that is the basic information about comparator circuit. So these are the comparator unit. Okay, as I mentioned just now, this is the input, both of them this input. One is always fixed, which is known as reference voltage. Okay, one can be changed. The value can be variable, can be changed. Okay, and then this is the DC supply to control the limitation of the output. And this is the positive values because this is negative, so the DC supply will be positive. So the value it depends, okay, how much value the DC supply value, and since that this is positive terminal, so it will connect it to the minus DC supply, which is minus 10 volts. Okay, so this is the output waveform will come out here. All right, so let's say V in for this case, yeah, V reference is 2 volts. Let's say the V in that you apply here is lesser than 2 volts, lesser than V reference here. The output will be, the output voltage, yeah, will be at low voltage level, which is near minus 10. Okay, near minus 10. So this is for, but this one, yeah, this one is best. If you want to decide this, you need to look at the configuration where the input signal is. If the input signal is at the inverting or non-inverting, okay, because the value will going to be different later on. Okay, later on kita tengok, ya. Let's say, yeah, if V input, so in this case, yeah, the input signal is at the non-inverting. In this case, the input signal is that at the non-inverting. So if the V in is lower or is lesser than positive 2 volts, which is the reference voltage, the output voltage will be low voltage level, which is near to minus 10, which is, it will be it will be minimum value, which is minus 10 volts. okay, which is saturation. It will become saturation at -10. It will not exactly as -10, but we will say it is near to -10. Right. So, but if V input is bigger than positive 2 volts, yeah, bigger than the reference value, the output voltage will be at high voltage level near to positive 10 here, positive 10 voltage here, which is the maximum. Okay, so it will be like this. Okay, if the input graph is, let's say, this is the input graph, this is 2 volts. So 2 volts, this is the input, yeah, the input. So this is the reference, 2 volts. So if it is lower than 2 volts, the output will be near -10, which is like this. This is 0, this is -10, okay, this is 10. Okay, so if it is lower, dia nampak macam ni kan? So this is when V in is less than positive 2. Okay, this is what going to happen if V in is more than positive 2. It will going to be maximum, which is positive 10. All right. So this is when the input signal is at the non-inverting. For the if it is opposite, the other way around, it will be the other way around. Okay, dia akan tukar. It will be the other way around. Okay, so if the input signal is at the inverting, okay, which is kalau sini positive, sini negative. So if V in is lesser than 2 volts, so it will be near positive 10 volts. Okay, if V in is bigger than 2 volts, so the output voltage will be near -10 volts. Okay, so be careful. You have to look at where the input signal is. Yeah. So the OP amp non-linear applications. So say again is very high. Okay, the gain is very high. So this is V in. Yeah, kalau just now if linear, A is V plus minus V minus, right? For V out. Okay, so for non-linear application, V out will be A V in minus with the V reference. Yeah, so if V in is bigger than V reference, if the input is at the non-inverting, V out will be positive infinity, but practically it will limits by the positive DC power supply. Okay, positive DC power supply. This DC and this positive DC power supply, yeah, which is usually VCC. And if V in, if it is lesser than V reference, V out will be minus infinity, but practically it will be limited by this minus DC value, which is minus VEE value. All right, I hope up until here is clear, right? So where can we use this comparator? Where can we apply this comparator? So the application of the comparator is very useful for the QRS complex in ECG. What is ECG? ECG is the electrocardiogram, okay, that detects your heartbeat usually, kan? Again, you can see that there is a high input and low input like this, kan? So this is Q waveform. QRS refer to combination of Q wave, R wave, and S wave. Yeah, S wave. So Q usually at this lower wave. Yeah, R is this high, dia punya high at the top here, at the peak here, and S is at the bottom here. Okay, so for this detection, yeah, of QRS complex ECG cardio diagram device, we need comparator to get the reading. Okay, to get the reading like this. Okay, because it's very hard for you to get get the want to read from this waveform. So you need to look at the output. So the output will represent here like this, yeah, VCC 1 minus VE 0. Okay, so this is the reference, the reference. Okay, bye-bye. So this is at the reference voltage. Okay, so from the reference voltage, so for at the reference voltage, you need to compare. So kalau if like this, yeah, the reference voltage is here. So you need to compare the input value if it is more or less compared to reference voltage. Okay, so it will then only you can plot. It will plot to the output voltage like this. Okay, so the output voltage you can see it is the value is 0 or 1 1 0 macam tu kan for the cardio diagram kan it already set the value as like a binary like that, right? Okay, so op-amp non-linear applications. So the open loop operation as a voltage comparator. So this is the what from the earlier we have learned before, yeah, for the linear applications. So this is what this is how you want to calculate the output voltage, right? So for the for the comparator, okay, for the comparator, so this V plus will be V in, and this V minus will be V reference, right? As I mentioned just now. So this is how you're plotting the transfer characteristic for the comparator, where V plus is bigger than V minus, the output is at the maximum positive limit, and when the positive is lesser than V minus, the output switch to the maximum negative limit. So this is what when you learn in when you learn at the linear applications kan. So same sama sahaja lah as the non-linear as well. So non-linear V plus is more than V minus, which is you just have to replace V plus as a V in, V minus as V reference, yeah. Okay, by make sure as well where is the input signal is, yeah. So then VO will be positive VO saturation. Saturation value is depending on the DC supply value, same as well as this two. Okay. Sekejap siapa yang baru cuba? Okay, so this is the practical transfer characteristic for ideal op-amp. Okay, positive minus VO saturation. Yeah, so this is the VCC, and this is the minus VCC just now, yang the one that here. So usually, the value of VCC will come to reach near this value, but maybe there is some case the value will become lower. Okay, depending kalau lah ada resistor or something like that, the value will not become exactly as DC, the one that DC that we applied. Okay, so it will be a little bit lesser. Okay, but it will become near. Okay, nearly. In practice, usually 1 or 2 volt will be less. Okay, you will get 1 or 2 volt less than VCC than the DC supply. Why? Because there is always noise inside, so you can't expect that the value is for the saturation value is exactly the same like this. Yeah, exactly the same at this point. Right, there are always 1 or 2 volts lesser because because of due to the noise, all those things. Yeah, it will distort the signal a little bit. Yeah, only one input reference will be connected to input of op-amp, while the other will be required voltage that need to compare. All right. So let's look at the non-inverting op-amp comparator. So same as summing and also previously, we have 2 types comparator. We have non-inverting and inverting, as I mentioned just now. So for the non-inverting op-amp comparator, so it will look like this. The input signal is at the positive terminal, which is at the non-inverting signal. So the configurations, okay, it will look like this. Okay, the negative or the inverting signal, okay, it's supposed to be fixed value, right? So fixed value. In some cases, the input signal, the fixed at the inverting terminal here, is look like this, where there is a parallel resistor connected, where one is grounded, okay, and the other one is connected to the DC supply here, So how to solve? Again, you have to use like previous that we have learned before, voltage divider reference. Okay, so you have to use the V Thevenin, R Thevenin to solve this equation. Okay, so you have to recap our previous lesson. Okay, so you will need to get the value of V here. So V Thevenin is equals to the V minus here. All right. Okay, which is will be the V reference. Oh, sorry. In this case, we're gonna call this V reference. Okay. So V reference in this circuit is positive 6. Okay, taken from the voltage divider here. So positive V saturation is equals to positive volts or 12. Okay, or 12, positive volt or 12, minus V saturation will be minus volt or minus 12. Okay, so when VI is greater than positive 6, okay, this one, so for a non-inverting, if the VI is greater than the reference voltage, okay, it will be positive V saturation here. Okay, if the VI, which is the input, greater than the value of reference voltage, which is 6 volts. So the value of the output here will be positive 12. Okay, and the LED, since that there is a LED here, so the LED will goes on. When the VI is less than 6 volts, the output is at minus 12 volts, and the LED goes off. Sorry, just give me a minute. Syifa tengok ampam. Okay, we buka ampam dulu. Alright. So it depends, yeah. If so if the LED how for you to decide the LED to goes on or less, it depends what is the input signal value. Alright, so to know what is the input signal value, you need to compare with the reference voltage. So once you you compare with the reference voltage, identify again what configuration it is. So if it is not inverting, so if it is VI is greater than V reference, so it will be positive saturation. Okay. Alright. Okay. So gini, next. So this is for non-inverting. Let's look for the non-inverting plug. Okay. So for the non-inverting op-amp comparator. So this is the example for this one. Okay, so let's do the example, sorry. Okay, so for this example, the V reference here is grounded. It's very simple lah. V reference is grounded, so it means that the value is near to 0. Okay, so it means that the V reference here is equals to 0 volts. So the input signal is the sinusoidal input signal. So this is the input signal. Okay, so how the output signal will be? So at the half positive cycle here, okay, the sinusoidal input signal, okay, the sinusoidal input signal here, since that at this point, since that the VI is bigger than V reference, okay, so it will looks like it will goes to positive VSET, which is positive VCC value. So the output signal will be like this, at this point. Okay, positive cycle. So if this is the input signal, now the input signal is lesser than the V reference here. So VI is lesser than V reference here. So it will be minus V saturation here. Okay, where the V saturation here will be depend on this value. Okay. So you need to, so this is how the output signal will be. All right. So this is the inverting. Okay. So let's look at the inverting op-amp comparator. So the for the inverting op-amp comparator, the input signal is at the negative terminal. All right, at the negative terminal or at the inverting terminal. Okay, so these are the configuration of the comparator. Okay, where the fixed value of voltage is at the positive terminal, which is at the non-inverting. And if you look here, the configuration is look at like a voltage divider reference, voltage divider. So you need to refer the voltage divider same as before, which is you need to identify the V Thevenin, okay, voltage Thevenin. So it will be the voltage reference here. Okay, so once you get that, so if VI input signal is greater than the reference V reference, which is VI is larger than V reference, the output will goes to minus V saturation, okay? But if VI is lesser than V reference, okay, the output voltage will go to positive V saturation here. Okay, so V reference in this circuit is positive 6, okay, taken from the voltage divider. So the positive saturation will be positive V or positive 12, okay, depending on the voltage DC supply here. The minus V saturation will be minus V or minus 12, okay. So when VI is greater than 6 volts, yeah, when VI is greater than 6 volts, the output will swing to minus 12 volts. So the LED goes off. Okay, so it is opposite way with the non-inverting here. So when VI is lesser than positive 6 volt, the output will become positive 12 volts. Okay, and the LED goes on, right? So these are the input. For example, yeah, this is in this situation, the V reference is grounded. So when it's ground, it's equals to 0. There is no voltage flow here. Okay, so this is the V reference. V reference is same with the x-axis. Okay, let's say in this case, yeah, in this case, V reference, how the graph is going to look like? Let's say the input is like this. Since that the V reference is not 0, the V reference will be the y-axis. It is easy for you to make the y-axis equals to the reference. So V here is equals to 6. Okay, V here is equals to 6. So if you want to plot the output, so this is the x-axis. So this is 0, yeah? So this is the reference. So if you want to plot the output, this is y. So the output will be at the positive, it will become minus 12. At the negative here, okay, once it is lesser than minus per reference, it will become positive 12. It will be like this, okay? So this is minus 12, this is positive 12, okay? So it is easy, it is easier, if you want to draw the output graph, it is easy for you to plot. Okay, so now if you plot the V reference at the input graph, okay, it is better for you to plot the value of V reference at the output graph, at the input graph, so that you can easily compare the input signal and the V reference, and straight away you can draw the output signal. Okay, but if the V reference is equals to 0, then it's easy lah. So you don't, because it's same with the x-axis. Okay, so in this case, V reference is equals to 0 volts. So the output signal will look like this. So when at the positive cycle, okay, at the positive cycle, which is the V input is larger than the reference, which is larger than 0, so it will go to minus V saturation. Okay, so at the negative cycle, at the negative cycle, where it is lesser than the V reference, so it will go to the positive value of saturation. Okay, so this value is depending on this value actually, yeah. So this value will be minus VEE, and V saturation value is depending on positive VCC. All right, if you have the value, if the they're given to you the value of VCC, then you put the value of VCC here. All right. Okay. Up until here is clear? Is it okay up until here? Okay, fine. I hope. Oh, okay. Kalau okay, because kalau okay, you can try to draw this. I think this is very simple because it is about drawing a waveform only. Draw the output waveform V0 for the given sinusoidal input as shown if V reference for here, yeah. This is the configurations. This is the input signal. Okay, so first of all, the V reference is equals to 0. Okay, so this is the reference equals to 0, and the next one, when the V reference is equals to Vm divided by 2. Okay, Vm value divided by 2. Okay, so let's solve this equation. Okay, the solution will be like this. Okay, so first of all, so first of all, Vref is equals to 0. And next, Vref is equals to Vm over 2. Okay, so this is the input signal, right? This is the input signal. So I think for the input signal, so that since that this is the inverting configuration. Okay, so this is the inverting configuration where the input is at the minus, so it will looks like when the Vm is same with the reference, bigger than the reference, it will be, the output will be minus VCC, all right? So when the input is lesser than the reference, it will be hit the positive VCC, okay? Since that the value is here, yeah? Next, I think for V reference equals to 0 is simple, okay? But when the V reference is equals to Vm over 2, so you have to draw, you have to get the value of Vm, and you have to draw the inputs, the reference line. So now the value of Vm value, and let's say 5, yeah? So 5 divided by 2. So 5 divided by 2. So draw the value of reference signal, reference voltage like this, yeah, like this. Okay. Yeah. Yeah. Okay. So from here, you can see that there is a value at the positive cycle which is lesser than the reference value, so it will be positive here at this point. Okay, and there is also and only a few value of the positive cycle will be bigger than V reference, so you will get only at this point it will becomes the minimum value of output value, right? So you have to very careful with this with this kind of questions when the V reference is not equals to 0. Okay, so that's why I advise to you for you to draw the line of V reference first before you solve this kind of questions. Yeah. So up until here is okay. Yeah. So let's proceed to the Schmidt trigger. So what is Schmidt trigger? Okay, usually comparator is very hard for you to get this kind of output value and this kind of input signal. It's very hard for you to get for you to get or for you to supply nice input signal without any noise. So comparator has always a problem with noise. Yeah, if input voltage is superimposed with noise, yeah, where the signal is distort a little bit. Okay, usually the signal is like this, right? But sometimes the signal is like this. Okay, if the input voltage is superimposed with noise, this will cause a false triggering. Okay, we call this false triggering. What is false triggering? So false triggering is incorrect change of incorrect change of state where the input signal, okay, there is a distortion at the input signal. Okay, there is a noise at the input signal. Okay, it makes the input signal not exactly sine waveform. Okay, so to overcome this is by using, okay, you can overcome this by using Schmitt trigger. Okay, you can overcome this by using Schmitt trigger. All right. Okay, for example, like this, yeah. Okay, so this is so this is the input signal. You can see the input signal here is there is a fluctuations. Okay, we call this fluctuations. Okay, that will that will distort the input signal. So if this input signal is not solved, okay, you will get false output signal, which you can see at this point. For example, yeah, the reference is at this point. So at this point, since that there is some of them is a little bit higher than V reference, and some of them is a little bit lower than V reference. So there is a false triggering here happen. Okay, at this at this point, and also at this point as well. Okay, which is at this point, yeah. Kenapa di sini? Okay. Right, at this point and at this point. So this is what we call the false triggering, where at the output, yeah, dia detect wrongly the signal, the input signal. Okay, they triggered wrongly the input signal. Okay, so that's why we need to solve this case, because if not, you will get wrong output signal. Okay, so yang ini yang dipanggil false triggering. In this case, we call it false triggering. Okay, unwanted fluctuations. Yeah, so Schmitt trigger provide hysteresis. Yeah, or two different threshold. Okay, Schmitt trigger, they provide hysteresis. Later on that we will look what is hysteresis is all about. Or two different threshold voltage level that we call the upper trigger voltage or lower trigger voltage. Yeah, that it will have two thresholds for this Schmitt trigger, where usually we have only one single one threshold kan, ataupun one threshold. But for this Schmitt trigger, we have two thresholds. Okay, to control this signal, this top signal, where it is we have upper threshold and lower threshold. Okay, so we have three types of Schmitt trigger actually. Selain daripada OP amp, we have different type of Schmitt trigger. We have logic IC Schmitt trigger. We also have transistor Schmitt trigger. Okay, and we also have operational amplifier Schmitt trigger. So compare logic IC and BJT Schmitt trigger. OP amp Schmitt trigger is the simplest one. Okay, is the easiest Schmitt trigger, because you can see Schmitt trigger for the OP amp, you need to just add the feedback. Only you need to add positive feedback. Okay, and you can have the Schmitt trigger already. Okay, at the comparator OP amp, you just add the positive feedback, then you get Schmitt trigger. So OP amp non-linear application for the Schmitt trigger. So comparator with positive feedback. Okay, so as mentioned just now, you just need to add positive feedback. Yeah, positive feedback okay, to form a Smith trigger. So no matter lah if the positive is reference or the signal is at positive, tak kira lah no matter if the signal is at positive or reference is at the positive, you need to add a positive feedback at the positive terminal, at the non-inverting terminal, okay, for you to form the Smith trigger. So in this case V reference is at the positive terminal, okay, and this is the non-inverting, betul kan? Sorry, this is an inverting comparator, okay. So in order for you to get the Smith trigger, you need to plus with the positive feedback, okay. So V plus is equals to V reference R2 over R1 over plus R2, and then VO R1 over R1 R2. So mana nak dapat ni? How to get this V plus value? Again, you need to use solve one by one, okay? You need to solve one by one, that what we have done just now. Okay, for example, at this point, I that flow here is same. I that flow from at resistor R1 is same with I that flow at resistor R2, since that this is an big impedance inside here. So I is equals to V in, sorry, V reference, bawah ni V reference kan, V ref minus, let's say this is this is V plus, V plus over R1, and then equals to, at this point pula, alright, V plus minus V out and over R2. Okay, so rearrange this equation, make the V plus as the mean equation, so you will get this equation. Okay, V out here, V out, V out, right. Okay, so when VI is lesser than V plus, okay, when VI is lesser than V plus, then, okay, same as inverting comparator, then VO is equals to positive VO saturation. Okay, so replace this VO with this VO saturation, okay, so it will looks like this. So this will be the upper trigger voltage. Okay, this value will be the upper trigger voltage, because this is for the inverting. Okay, inverting, kalau inverting, if VI is lesser than V plus, tak boleh jalan. Okay. Oh, sorry. Okay. So if V plus is lesser than V signal is lesser than V positive, V reference, then it will become positive. So it will be, maksudnya when the signal is like this, since that VI is lesser than V reference, so it means that it is at the negative cycle, so it will produce the VUTP. So UTP here is a short form of the upper trigger voltage. So if you want to draw the graph, it will look like this. Okay, so this is the VUTP, where you need to be careful with the arrow here. The arrow is like this. Okay, dia ke arah, it point to the left hand side. So if VI increases, the output voltage, which is VO, is equals to positive VO saturation, and it will stay at this value until until VI, the value of VI just now, equals to the value of VUTP, where you have calculated just now, this one. Okay, it will stay until the value of VUTP, which is at this point. Okay, and beyond this point, if VI keep increasing, okay, then VI is larger than VUTP. What we're gonna do, what we're gonna happen is the value we're gonna be dropped. Okay, then VI is larger than UTP, so VO will change to automatically will change into V output saturation, the V of minus the DC minus value here, yeah, VO saturation. Okay, so this you will get this, yeah, for this value. Okay, so once the VI value, okay, bigger than VUTP, it will drop, yeah, it will drop and it will go to the VO saturation. Okay, what will happen for the other way around pula? Okay, so when VI is bigger than VUTP, output will be VO equals to minus VO saturation. Then the output at the V plus terminal, it will become V reference. So you have to change just now. You're gonna same use. How to stop this? Okay, so it will become VO saturation, and it will become minus, yeah, and this will be the lower trigger voltage. Okay, lower trigger voltage. What will happen? VO is equals to minus VO saturation and stays as long as this value. Okay, it will stays at this value. So VI is bigger than VLTP, but if okay, so it will stays at this value, yang ni dia akan ke arah this pula. Okay, when VLTP, the graph will pointing to the left hand side. Okay, left hand side. Okay, so it will stays at this value. It will stays at this value, negative, 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 negative. But once the VI is reduced, which is keep reducing, yeah, until VI is very less than value of VLTP, it will start to become VO saturation pula. Okay, it will start to become VO saturation pula. So it will be maximum. Okay, it will start to become maximum. Okay, so now dia macam confused, right? It was confused, right? Because just now it's like this, and now it's like this. Just now it is like this, and now it is like this. So let's look the combination. So the combination is like this. Okay, it will start at this point, for example, yeah, it will start at this point. Okay, so when the UTP first, yeah, when VI is bigger, sorry, this is when VI is within the VUTP, yeah, so it will be at this point. Okay, once VI is bigger than VUTP, it will start to drop and it will go this way. Okay, it will go this way, and then now you have to calculate for the VLTP pula. Okay, so for the VLTP, okay, when the VI is lesser than VLTP, from here it will goes to this part, yeah, it will goes to this part. Dia akan jadi negative VO saturation, and then from here, when the VI is bigger than VLTP, it will automatically goes up and it will goes near to the VO saturation. So the first cycle is actually like this. The cycle is actually like this. Macam ni, macam ni, macam ni. Okay, the cycle is actually like this. Okay, from here it will start another cycle pula dekat sini. Here it will start another cycle pula dekat sini. So the cycle is actually like this, yeah. So this is what we call hysteresis cycle. Okay. So this shows that when VI is bigger than is lesser than VUTP, then V output will be positive VO saturation. If VI is larger than VUTP, it will start to change, yeah, minus VO saturation. And at this point, compare VI with, at this point, we need to compare VI with VLTP pula. So we use the same equation, but you have to just gantikan sahaja. You have to replace the this VO value with the minus VO saturation, yeah. So that's why it becomes minus, yeah. And then VO saturation. And if VI is larger than VLTP, then VO will become VO saturation. Sorry, ni VO saturation. This is supposed to be minimized. Yeah? And if VI is lesser than VLTP, then VO will become V positive saturation. Okay. So in this situation, there are two reference. Yeah, there are two reference actually. Kita ada two reference here, which is one is UTP, one is VLTP. Okay, one is UTP, one is VLTP. So this is the two reference here. Alright, that will limit the output voltage. Okay, but just now the reference is V reference as the the DC voltage will be the limitation of the output signal kan. But now the reference ataupun the limitation is based on this VLTP value and the VUTP value. Okay, it will be limited by that value. Alright. So for the hysteresis, yeah, you need to know how to draw and how to explain. I mean, you need to know how to draw this graph, and this equation is based from the earlier inverting equation. And so what is hysteresis again? Hysteresis means that there is a higher reference level when the input voltage goes from a lower to higher value, and when it goes from a higher to lower value. So this is UTP and this is LTP. Yeah, so the two reference are UTP and LTP. Upper trigger voltage, betul. Upper trigger voltage and lower trigger voltage. Yeah, upper trigger point, lower trigger point. Yeah, it is desirable characteristic because it prevents the comparator from the switching back and forth in response to random noise fluctuations. Yeah, and quantitatively the hysteresis voltage, yeah, VH of a Schmidt trigger is defined as the difference between the input trigger levels. So if you want to find what is the VH ataupun the value of hysteresis voltage, so the value of hysteresis voltage is the upper trigger minus with the lower trigger. Okay, the upper trigger minus with the lower trigger. And from this equation, you can simplify. It will become like this. All right, it will become like this: R1 over R1 plus R2 plus VCC minus VCC. Okay, so here are the example. Okay, so let's look at the example here. If V1, okay, is equals to 10 sine omega time, okay, omega times volt, yeah, determine the VUTP and VLTP. Okay, sketch the output waveform and the transfer characteristic. So it's given to you the value of the input signal. So based from the formula, okay, VUTP and VLTP, okay, based on the formula, you can find straight away VUTP and VLTP. I believe there is no problem for here. And then what you need to do is you need to sketch the output waveform. Okay, for in this case, you need to sketch the output waveform. So the output waveform, yang ni dia tak look macam ni sikit ya. It's actually continuous, and then but because I'm using computer, so nampak macam tak sama sikit this part. So it's actually ni. Okay, so first of all, 8.67 volts. So 8.67 volts. So this is the input signal. Yeah, this is 10. This is minimum minus 10. This is positive 10. And so this is going to be the VUTP. Okay, this is going to be the reference voltage. Now the reference voltage is VUTP. Okay, and the for upper trigger lah. For lower trigger, we're going to be VLTP. So this is going to be like this. So again, the output, yeah, macam yang kita, as we learned just now, since that this is the inverting. So if the value is lesser than the reference value, okay, it's lesser than the reference value, it will be the maximum, right? It will be the maximum. So at this point, it will be maximum, yeah, kat sini. Kat sini it will be maximum. For at this point. So it will be bigger than the reference value, kan? So it will be minimum point. So at this point too, it is bigger than this reference value. So it will be, sorry, it is lesser, sorry, because this is negative part, kan? This is negative cycle. So it is lesser than the reference voltage, lower trigger point value. So it will be maximum. Okay, so kena tengok, you have to recognize to look at which trigger point. So for this negative cycle, you need to based on LTP. For this positive cycle, based on UTP. Okay? Okay, tak? I hope it's clear for this one. I think for the next class, we will discuss more about the example for this Smith trigger especially, and also a little bit discussion for the linear amplifier as well. So for next class, we will discuss more about questions. So before we discuss that question, I will upload first during, I hope I can upload during by the day after tomorrow, by Thursday, the questions first, and then I want you to try first, and then we will discuss on the on Monday. Is it possible? So that we can check either you understand or not the questions. Is it okay? Any questions regarding Smith trigger and comparator? Actually, we have finished the chapter 6. Alright, so to check this today's lesson understanding, I will upload later on the questions, which I will take from the previous questions, previous tasks, and bank questions. Okay, so I will upload and we will discuss it on Monday. Is it okay? Alright, so we start the class earlier now, 10 minutes earlier. If you have any don't have any questions, so I can end the class today. Thank you for your attention. Thank you. Assalamualaikum.
Arigato sensei. Thank you.
Thank you.
Thank you, Sensei.